Then hello everyone, it's my great pleasure to welcome all of you to our international online seminar on interval methods in control engineering. And today's speaker will be Théo Le Terrier from the Rainbow team at IRISA in Rennes. And Théo completed his studies in 2023 at the Télécom Physique Strasbourg, an engineering school. And before starting his PhD, this was before starting his PhD in the Rainbow team in Rennes. And there he's supervised by Marie Babel and Vincent Trevel. And we're now looking forward to your presentation, Théo, about a sensor-based safe navigation of a powered wheelchair using interval analysis. The floor is yours.
Okay, so thank you very much for this introduction. As you said, I'm going to do this talk about sensor-based safe navigation for a powered wheelchair using interval analysis, and I will present different aspects of this navigation framework, from the localization to the control of the powered wheelchair. And so first, I'm going to give you a bit of context about the work I'm doing in my PhD. So my PhD is the continuation of the so-called Ambrosian project. So this project is about power wheelchair autonomous indoor navigation. So an example of what was done in this project is shown in this video. So you can see a power wheelchair autonomously navigate from a charging station to the bed of a user for transfer. But you can think about other use cases. So for instance, you can think about sending the power wheelchair away from the shower of a user to avoid the water. And then when the user is finished with his shower, then bring back the power wheelchair to proceed to the transfer. And you can imagine many different use cases that would help increasing the autonomy of a potential user. So this is what the Ambrosian project and my PhD is about. So we want a safe navigation system for a power wheelchair. So when we design a navigation system for a power wheelchair, we have some design considerations. So in my PhD, we want to interface to commercially available power wheelchair. We also want low cost and easy to install sensors for the acceptability of the user. And with these considerations, in my PhD, we are using ultra-wideband sensors for indoor positioning and course navigation, and time of flight infrared sensors for obstacle avoidance. And so in the first part of this talk, we are going to focus on ultra-wideband sensors for indoor positioning and course navigation. And so the first part that we are going to see in this talk is how do we do a positioning system using ultra-wideband sensors. So a typical setup for ultra-wideband positioning is the one I'm showing in this picture. So basically you have several fixed sensors that are called anchors, and their positions are assumed to be known. And you want to localize a mobile sensor that is called a tag. And so how do you do to localize this tag? You use the distance measurement between the tag and all the anchors in your setup. And so how do we measure the distance between the tag and one anchor? There are several techniques, but in my PhD, we use sensors that leverage the two-way ranging technique. So basically, I'm just going to present a simplified scheme of the two-way ranging technique. But let's say that you have a node A that wants to measure its distance to a node B. Then it will send what's called a range request to the node B. And the time taken by the signal to go from A to B is called the time of flight. Okay? And we want to measure this time of flight. Then after a certain time, the node B will send an answer to the node A. And again, the time taken by the signal to go from B to A is the time of flight. So this response time, RT, is known. We also can measure the total round-trip time of the signal. And with this, we can compute the time of flight and then the range between the two nodes. So this is how we perform the distance measurement between our tag and the anchors in the setup. Okay, and how do we use these distance measurements for the localization of the tag? Well, let's see how we do this. So let's say the tag set a range request to this anchor, the anchor replies, we compute the distance is measured, then all I know is that my tag is located on this circle. So the center of this circle is the anchor's position, and the radius of this circle is the measured distance. So with only one anchor in my setup, I don't have a lot of information. But if I put at least three anchors in my setup, I am able to have a unique solution for the position of my tag. Okay. I represent the setup with 4 anchors because this is what we used in the work I'm going to present. Okay, but here I have a way of having a unique solution for the position of my tag. But we are not interested in localizing a single tag. We want to estimate the pose, so the position and orientation of our power wheelchair. So the idea basically is to equip the power wheelchair with several tags, at least 2 for the orientation. And if you know the position of the tags with respect to the local frame attached to the power wheelchair, then you can estimate the pose of the power wheelchair using this ultra-wideband positioning system. Okay, so we have a way to estimate the pose of our power wheelchair. But here I presented the case where the distance measurements are perfect. So the case of ideal sensors. I explained at the beginning of the presentation that to increase users' acceptability, we use low-cost sensors. And of course, low-cost sensors comes with a lot of sources of error. So for instance, we have all the random noise. We have also systematic biases. So we are usually dealing with uncalibrated sensors. Also due to the antenna pattern, the 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 bias depends on the orientation of the sensor. Hence, it depends on the pose of the power wheelchair. There are many different biases that should be taken into account. So another source of error. And we also have what is called spurious measurements. So I did not say it earlier, but when you do a two-way ranging technique, you assume that the path followed by your signal to go from the tag to the anchor is the straight line between your tag and your anchor. And this is called the line of sight path. But in a real scenario, you can have obstacles masking this line of sight path. So for instance, the obstacle can be a wall, it can be a furniture, it can be the power wheelchair itself. And when you have an obstacle masking the line of sight, then what you can measure is, for instance, a reflected signal. So this signal that is reflected on the wall, for instance. And then you will measure a distance that is greater than the actual distance between your tag and your anchor. So this is an interesting property when using ultra-wideband sensors. It is that we know that the errors coming from non-line of sight signal propagation will provide measurement distance that are greater than the actual distance between the tag and the anchor. Okay, so we have all these sources of error, and what we want to do with this is not to design a set membership power wheelchair pose estimation method that provide a confidence domain of the pose of the power wheelchair. So we want to provide a set of power wheelchair pose that are consistent with our uncertain measurements. So again, when I'm talking about the pose of the power wheelchair, I'm talking about the position and the heading, so the orientation of the power wheelchair. And in this work, we assume no prior knowledge on the power wheelchair configuration. We have no idea where it is initially located and how it is initially oriented. And for this, the only thing that we have are our range measurements and this simple observation model. So the range between a pair of anchor and tag is the distance between the anchor and the tag plus a certain range measurement error that is unknown. And so you can see that this observation model depends on the pose of the power wheelchair. And the next thing that we want to do to design this robust positioning method is to have a model for this ranging error term. And so to this, we could use the data provided by the constructor to provide a bounded error model. But so here I show some data provided by the constructor for the distribution of ranging error. But these data comes from a very laboratory conditions, so with calibrated sensors and in almost perfect line of sight conditions. But in reality, the calibration of the sensors is very hard to achieve because you have the power wheelchair, the walls that can mask the line of sight. You have also the calibration that is you have a systematic bias that is dependent on the orientation of the power wheelchair. Also, at the beginning of the presentation, I said that the position of the anchors are assumed to be known, but in reality, they are just coarsely estimated. So again, this introduces another bias that is difficult to identify. So we cannot reasonably use this data to provide a bounded error model for our ranging error. So what we did was that we performed the data acquisition in a room. So the room was equipped with a motion capture system, and it was also equipped with 4 ultra-wideband anchors, basically at the corners of the room. We used a real power wheelchair equipped with 4 tags, and the power wheelchair was manually driven inside the room. So the range measurement were recorded, and also the ground truth provided by the motion capture system. And with this, we computed this histogram of ultra-wideband ranging measurement error. So you can see that it is not like the one provided by the constructor. So we have greater error, and some of them are also coming from non-line of sight signal conditions. Okay, so let's have a look at this histogram a bit more. So we can clearly distinguish 2 parts on this histogram. So you have this green part that corresponds to the ranging error coming from line of sight conditions. So basically in this part of the histogram, the ranging error can be modeled by a centered interval. It just means that each measurement error term between a tag and an anchor should belong to a certain interval. And then you have another part in the histogram, so this red part that corresponds to the errors coming from a non-line of sight signal propagation. And then, as I explained earlier, due to the positiveness of outliers coming from non-line of sight signal propagation, we know that the lower bound will remain satisfied, but the upper bound here will be violated because of the non-line of sight errors. Okay, so a thing that we could do to provide a robust positioning method will be to use a Q relaxed intersection scheme. But since we know that we have some positiveness on our outliers due to non-line of sight properties, what we can also do is to keep a single bound, and then just to keep the bound that remains satisfied. So let's do this. So we keep only the lower bound on the ranging error, and this define for each pair of anchor tag a set of range upper bound constraints. And so these constraints are almost always satisfied, as you can see here on this picture. So now I'm going to just explain how this set of constraints works. And for this, we are first going to consider the case of an ideal sensor with perfect distance measurement. So basically, I have the measured distance between the anchor and the tag. And what does this constraint says? It just says that my tag is located inside this pink disk. So the center of the disk is the anchor position, and the radius of the disk is the measured distance between the tag and the anchor. So I have not a lot of information here, but with my four anchors in my setup, I am located at the intersection of the four disks, and then I have again a unique solution for the position of my tag. And this is not longer the case when we exit the polygon defined by the ultra-wideband anchors. As you can see here, even though we are considering ideal sensors with no uncertainty, the solution here for the position of my tag is a set. So of course, if we use this set of constraints to provide confidence domain outside the anchor's polygon, we will provide a too conservative confidence domain. But in real life scenario, you usually install the anchors in the corner of your room. So it's a reasonable assumption that you will not exit the anchor's polygon boundary. So let's do this assumption in the following, and now let's consider the case of real sensors. So with uncertainties. So of course the set of the higher the uncertainties, the higher the volume of the feasible position set. Okay, and it's getting worse as you approach the anchor's polygon boundary. Okay. And then from this set of constraints, we can define what is called a separator, so SUB for range upper bound, and then use an algorithm such as the CVA algorithm to construct an inner and outer approximation of the solution set, resulting from this set of constraints. Okay. So here we have a way to provide a robust solution, to provide a confidence domain of the pose of our power wheelchair without using any Q-relaxed intersection scheme. But just to continue this talk, if we want to extend this method to the entire geometric space, so outside the anchor's polygon boundary, or if we just want it to provide less conservative domains when we approach the anchor's polygon boundary, we can add another set of constraints. So this time, if we keep only the ranging upper bound here, we can define the set of range lower bound constraints. So of course, this set of constraints are satisfied only in line of sight condition. As you can see here, they are violated with error coming from non-line of sight errors. Okay, so if you want to incorporate them in the positioning method, then we have to use some Q-relaxed intersection on this set of constraints. So I'm not going into detail for this set of constraints, but again, we create a separator, SLB for lower bound, for the Q-relaxed intersection of all tag anchor pair constraints. And with this, we can define two different reliable positioning methods. One that will be called the SUB method, and then that only use the separator for the set of range upper bound constraints, and the S method that use a separator that is defined as the intersection of SUB and the separator for the Q-relaxed intersection of the Q-relaxed set of range lower bound constraints. Okay, and so I'm going to present some results on these two methods. And yeah, just so you know, the solution sets are here computed with the CV algorithm using the Kodak library. Okay, so if you remember at the beginning of the presentation, we saw the power wheelchair inside a room, and I told you that during the experiment with the motion capture system, the power wheelchair was manually driven using its joystick inside the room. And so on the right, you can see in red the path followed by the power wheelchair during this experiment. Okay, you can see the anchors in the room. Okay, and what I'm going to present here are some confidence domains. Okay, so outer subpavings computed with the CV algorithm. So computed with the SUB method in orange and the S method in green. Okay, and I'm going to present some results for two different poses during the experiment. The pose A, that is a pose that is far from the anchor's polygon boundary, and the pose B, that is close to the anchor's polygon boundary. So when we are far from the polygon, you can see that the SUB method provide almost identical confidence domain as the one provided by the S method. So this shows that when we are far from the polygon boundary, then the set of range upper bound constraints provide good results, even if we are not using any Q-relaxed intersection scheme. And then with the B method that is close to the anchor's polygon, you can see that as expected, the SUB method provides more conservative confidence domain, and that the set of range lower bound constraints help further reducing this confidence domain. Okay, so this is what we expected, but yeah, this was validated through experimental data. Okay. Then the next thing that we did was to assess the reliability of our interval methods by verifying for each measurement epoch if the computed confidence domain contains the post-ground truth provided by the motion capture system. And so here I present some results of integrity. So over the whole data set recorded during the experiment, we obtained these results of integrity. So as you can see, the SUB method provides slightly better integrity result than the S method, but yeah, this is normal because we just added more constraints for the S method. But what is really interesting here is that we obtained a good integrity results despite the fact that there is no QRelax intersection in the SUB method. The robustness of the method is inherent to the constraint formulation. So we used the positiveness of our outliers to provide a robust method without QRelax intersection. Okay. And then you can also see on this picture some pose estimate. So what we did was that we took the centroid of all subpaving boxes as a pose estimate for the power wheelchair, and then we compared it with the post-ground truth. And here I can present some cumulative distribution function for the planimetric error for the two methods, so the S method in green and the SUB method in yellow. So again, as expected, the S method provides a slightly better accuracy result than the SUB method because the accuracy is increased when the power wheelchair is close to the anchor's polygon boundary. But for the two method, we have a sufficient accuracy result for our application purpose. That is the course navigation of a power wheelchair. Okay. So to summarize the first part of this presentation, I presented a set membership ultra-wideband-based reliable positioning method that provide consistent pose domain and sufficient pose estimation accuracy for course navigation of a power wheelchair. So we have seen that within the anchor's polygon, we can obtain a robust solution without using Q-relaxed intersection. Just using the positiveness of outliers coming from a non-line of sight signal propagation. And we have seen that we could extend this approach to the entire geometric space using a set of Q-relaxed constraints that are verified only under line of sight conditions. Okay. So this method, the confidence domain provided by this method could be used, for instance, to focus the initialization step of localization method that needs a good initial guess, for instance, a particle filter. But the next thing that we are going to ask in for this second part of the presentation is, can we design a power wheelchair control law that explicitly accounts for pose estimation uncertainties? So why this will be interesting? This is because if I recall our goal here, we want to control the power wheelchair to target pose while ensuring robust obstacle avoidance. Okay, and so if we want to ensure robust obstacle avoidance, it may be a good idea to take into account the uncertainty in the pose estimation of the power wheelchair. So in this preliminary work, we are going to make some assumptions. So first, the obstacles are static. There is no dynamic obstacles such as pedestrians. The obstacle positions are assumed to be known. And yeah, we have a pose estimation method that provide confidence domains of the pose of the power wheelchair. So for instance, the one I presented earlier. Okay. So we want to do power wheelchair control. We want to control the power wheelchair. So for those who may not be familiar with control, I will just summarize what we want to do. So we have an estimate of the pose, okay? So this comes from what I presented earlier, for instance. So you have your ultra-wideband measurements, and then you have a block that use these measurements to provide a pose estimate. So this is what I presented earlier for the robust positioning method. Then you also have your target pose. So for instance, it can be a pose next to the bed of a user for a transfer. Okay, and this defines an error between your target pose and your currently estimated pose. And so now the thing we are going to focus on is this controller block. Okay, and so the idea is to compute the control vector, so that is composed of the linear velocity and angular velocity that we want to apply to the power wheelchair to make this error converge to 0. Okay, so we want to design this controller block. And of course, we are going to incorporate some constraints in this block. So first of all, the obstacle avoidance constraints, but also some other constraints, such as the physical actuators limit, and also the comfort of potential and control. Such constraints is the model of your system and the here on this slide. Okay. Okay. So typical problem formulation. So basically, when you you create your system using the evolution model to optimize of future control action to to obtain the best performance constraint system. So the idea is to minimize function. Okay. So I will constraints on your control input, and the predicted maybe the color avoidance constraints, the constraints predicted control will be um, user comfort. For instance, linear of your platform. Okay. So formulation, simple the target. So I have an obstacle predicted pose. Let's just assume that we measure pose of the power wheelchair. For instance, is the solution return NMPC resolution. This is the predicted trajectory, and you can see the obstacle optimized view of the control because the model is a little bit from the and then that you obtain new measure the current pose of your power chair. This for each measurement. So we the NPC apply the first value until hopefully we okay. But it's perfect. But no, we error in our pose. Okay, here depicted in black and orange. So if the NPC the obstacle, but equal. Okay, so the obstacle follow the predicted trajectory, then it will collide with the obstacle. So the idea is to consider the confidence domain provided by the instance provided by the position presented earlier, and then to construct an enclosure of all system trajectories over the predicted horizon to ensure that the obstacle avoidance constraints are satisfied for all possible trajectory variation. Okay, so let's see a bit how this is going to work. So we have the target pose here, the obstacle here that we want to avoid. And first, we just solve the nominal PC problem with the obstacle avoidance trajectory that a predicted trajectory that we can obtain. Okay, but this is the estimated wheelchair pose. But in reality, all we know the power wheelchair lies in this box of physics are consistent with the uncertain measurements. Then from the NMPC solution, you have this optimized control. Okay, and so the idea is to protect the uncertainties over the prediction around model. Okay, so let's do this. So we have the optimized control sequence. We have some bounded error model for this. Then using the uncertain evolution model, the uncertainties over the prediction horizon. Okay, we can compute an enclosure of all feasible trajectories of an horizon. And here we can see that the predicted and trajectory collide obstacle. Okay, so constraint is not robustly satisfied. So the idea is to modify the uncertainties. Okay, so of course we have to do the uncertainty boxes over the prediction horizon. Just for the example, I'm going to put these three boxes next to the obstacle. And so basically we inflate the obstacle to take into account the predicted uncertainty on our prediction horizon. Okay, so this will be the inflated obstacle, but still to keep things example, we are going to over approximate this inflated obstacle by a circle, gear circle. Okay. And so now is to solve again the NC problem with updated constraints to take into account the predicted uncertainties. And so now you have, if the solver function, then you have predicted avoids the inflated obstacles, and then you can keep going, predict the uncertain trajectory over the prediction horizon, and then you just have to check if the predicted uncertain trajectory collides with the obstacle, or if it does not collide with the obstacle. So if it does not collide with the obstacle, then the obstacle avoidance constraint is robustly satisfied, and you can apply the first value of the optimized control sequence. And if the uncertain predicted trajectory still collide with the obstacle, then you can keep repeating this process. Okay, and then you can continue to do this until you converge to the target pose. Okay, so this was a simple example. And now I'm going to present some very preliminary results on this work, so in simulation. So this is the simulation environment. So we have a simulated power wheelchair equipped with 4 tags. There are 4 anchors in the simulation world. We have 1 obstacle, and we want to drive the power wheelchair to the origin of the simulation environment. Okay, and I'm presenting this for the robust NPC controller with the updated constraints on the left, and on the right, I'm presenting result with an NPC that does not take into account the pose estimation uncertainty. And you can see that on the right, the power wheelchair collide with the obstacle, and it is not the case with the robust NPC controller that use the predicted uncertainties to inflate the obstacle. Okay, so these are very preliminary results. Okay, of course it has limitations. So the obstacles are assumed to be static, but most importantly, their positions are assumed to be known. And yeah, this I think is a drawback. So in recent works, during my PhD, we designed an ultra-wideband-based non-linear model predictive controller using the infrared time-of-flight sensors I presented at the beginning of the presentation for obstacle avoidance. So in this work, we integrated the time-of-flight sensors for the obstacle detections. I'm going to present some results on this work, but just so you know, the uncertainties on the pose estimation are not considered in the work I'm going to present. Okay, so this is some result that we very recently obtained. So here you have the power wheelchair equipped with the tags and the infrared time-of-flight sensors that have to pass this very narrow door. Okay, and the obstacles are detected using the infrared time-of-flight sensors. And you can see that it managed to pass this narrow door and avoid the steps uh, in a good way. Okay, and so it has to the target poses behind the pile of steps. Okay, so this is an example of the work we have done recently. Another example is this one. So the power wheelchair has to navigate in a really cluttered environment. Maybe on the video you don't see well, but it's a very cluttered environment. It's even for a human in the power wheelchair with the joystick, it's so difficult to navigate here. But still, the power wheelchair may navigate in this cluttered environment and to reach the target pose. Okay. But as I said, here there is no pose estimation uncertainty taking into account. There is no uncertainty on the infrared time-of-flight sensors measurement taken into account. And so the future works in the next year of my PhD will combine both approaches to design a broad NMPC-based navigation system for power wheelchair in a cluttered environment. Okay, and to conclude this presentation, I presented a reliable ultra-urban-based positioning method for power wheelchair that provide confidence domain of the pose of the power wheelchair. And then I presented a way of using these confidence domains to design a robust, low-cost, ultra-urban sensor-based model predictive control with obstacle avoidance constraints. And yeah, I also presented some results, some recent results on NMPC-based navigation using the infrared time of flight sensor for obstacle detection and avoidance. Okay, thank you for your attention.
Yeah, and many thanks to you for your very interesting and also, yeah, quite intensive discussion about the possible questions concerning localization and also model predictive control design. I think it was highly inspiring for the audience. Now, who has questions? Be quick. I'll try to ask my question.
Yeah,
Okay, in the first part of the presentation, you did this
yes.
localization with or without the QA relaxed approach. And each time you have a new measurement, you're doing a new localization. In the model
Yes,
predictive control, you know that your wheelchair is following a continuous trajectory. Do you have any idea how to
yes.
implement a strategy that allows to implement something like a predictor corrector approach for the localization? Firstly, localizing a domain, then forecasting how it will move into the future, and then use this already as an initialization for your calculation of the boundaries for the separator calculation in order to reduce the effort.
Yes. So we have done so without model predictive control, but we have done a work that exploits the control input sent to the power wheelchair to have a yeah, initial guess for the confidence domain. If this answer a bit your question. So this is not what I presented. This is not the positioning method that presented here. But yes, of course, we could use more information on the control inputs sent to the power wheelchair and maybe also predicted over the prediction horizon to start with a smaller set of feasible pose.
Okay. Yeah. And the other question is maybe of interest for the audience because I've already seen the wheelchair in real life. How computational costly is your implementation? What do you need really as a hardware in order to run all those things, the MPC and also the localization?
Um, yeah, I cannot like really answer this question. No, I'm using my computer that is yeah, it has uh, really enough computational power to do what I want. But so in the simulation results I presented, clearly I think so these are old results, but it was 5 hertz control, okay, and the 200 milliseconds were used by my computer for solving the model the NPC problem. And in the work I presented, in the recent results, we switched to a real-time iteration scheme, and now I was able to run an NMPC navigation at almost 500 hertz. And in the work I presented, we limit the control frequency rate at 20 hertz. So I think with something like a Raspberry Pi, it will be enough to compute to run this navigation framework. But
Yeah.
yeah,
But I
we
think
want
already
to
this
see
answer,
this is
yeah,
something we are going to do in the
yeah.
yeah.
Also, already this answer is, I think, quite interesting for the audience since maybe someone would expect that you really have something that would require either a cluster of computers or that would require a GPU to get everything running. But I think it's really impressive to see, yeah, how quick everything that is required here can be evaluated. And yeah, I think that's impressive.
Thank you.
Okay, now I think we have arrived at the end of today's presentation. Many thanks again, Theo, for your presentation. And yeah, we'll continue our
Thank you.
online seminar on Friday, the 5th of December. And until then, have a good time, have a nice Friday afternoon, and nice weekend.